Hello everybody, welcome to the video lecture on refrigeration cycle. Today's is lecture 2, and today we are going to talk about ideal vapor compression refrigeration cycle, and also would like to see that how the actual vapor compression refrigeration cycle is different from an ideal cycle. So let's go ahead and start with the ideal vapor compression refrigeration cycle. So in the last class we talked about the Carnot cycle, right? um, this cycle is reversed. Carnot, excuse me. Right, so in the last class, when we saw that Carnot cycle, we saw that impracticalities in the compressor, which is liquid is input, and also the turbine, right? So these two was the impracticality. So today, those two in today's topic, ideal vapor compression refrigeration cycle, will see that how these two impracticalities is eliminated. So the number one, it's the compressor, right? So the compressor impracticality eliminated by vaporizing the refrigerant completely before entering the compressor. That means at point 1 it's completely vaporized, right? So it's saturated vaporized or superheated vapor. So it's vaporized, so then compressor can handle only the vapor phase. Okay, so it doesn't have like two phase anymore. And then second thing is that turbine is replaced by a expansion valve or throttling valve, right, to remove to eliminate the difficulties of the turbine blade. Okay, so we replaced this turbine here using a expansion valve. So that's the difference between the ideal or reversed Carnot cycle versus ideal vapor compression cycle. So now we can see that this cycle also comprises like the two phases. One is that liquid, another is the vapor, right? However, we are compressing the vapor here, so according to that process, the cycle name is vapor compression refrigeration cycle. So in following topic, or in upcoming classes, we'll use the VCR, vapor compression refrigeration VCR cycle. Okay. um, so now let's take a look at how this vapor compression refrigeration cycle works, right? So in actual case, how it works, or what is the working principle. So basically you can see that compressor, the vapor, refrigerant vapor is coming to the compressor, and then compressor task is to pressurize that vapor. So that pressurized vapor is passing through a condenser, right? Like copper tube condenser. What is happening here, when it's passing through the condenser, it's rejecting the heat, right? So rejecting the heat, and it's becoming liquid. So and it started to become liquid, and then still it's not liquid, but it's a low it's a high pressure. However, it's high pressure low temperature gas. And then high pressure low temperature gas is expanding through a expansion valve right here. When it's expanding through a expansion valve, pressure is further reducing and temperature is further reducing, so it becomes low temperature as well as low pressure liquid. So whenever that low pressure low temperature is liquid passing through a evaporator, then what it's doing, it's absorbing the heat from that surrounding environment, right? So basically, if you imagine that if you have a closed chamber here, and outside of the chamber or one of the wall is the evaporator wall, then what is happening, this from this space, basically it's absorbing the heat, right? And then making this space cold, right? So now absorbing the heat, it's becoming again the vapor or superheated vapor or saturated vapor that represent, and again it's going through the compressor. So that's how it's maintaining the cycle. So in our domestic refrigerator, how do we what do we see? So you will see that if you touch like one of the side wall or on the back wall, you will see it's pretty hot. Why? It's because of the condenser outside, or the wall or side wall or the back wall, rear wall. You will see that condenser rejecting the heat, so that's how we feel hot, right? Whenever we open this the top door or the bottom door, then we'll see that it's cold space. We maintain the temperature low. How is it possible? Because the evaporator coil is embedded within the wall, so then it's basically extract the heat from those refrigerated space, or basically that closed space, right? So by extracting the heat, it's basically creating the refrigeration effect. And then there are four basic component, and the bottom of the refrigerator you should see the compressor, right? So that compressor is basically delivering the refrigerant through the condenser. And then you will see this capillary tube, like very small coil type capillary tube, you will see that. So that's basically the expansion valve, or throttling valve in that refrigerator. So these four key component you could easily find in your refrigerator. So basically, again, I would like to write one more two point. So from the Carnot cycle and the VCR, the difference between reversed Carnot and ideal ideal va- excuse me ideal vapor compression refrigeration cycle is: number one, compressor inlet is vapor. Okay, no longer liquid. Compressor inlet is vapor. Number two, turbine is replaced by expansion valve. Okay, so that's the difference between the reverse Carnot cycle versus vapor compression refrigeration cycle. So now let's take a look at vapor compression refrigeration cycle. What is the TS diagram? What is the energy balance equation, right? So this is the actual again I took the actual vapor compression ideal vapor compression refrigeration cycle. So if we draw the TS diagram, so before drawing the TS diagram, I would like to write some point, right? So 1 to 2, this is a compression process, right? So 1 to 2, it's compression process, and that compression is a isentropic compression. And 2 to 3, it's basically heat rejection right here. So that heat rejection is constant pressure heat rejection. And then from 3 to 4, that basically the expansion, right? So 3 to 4, it's throttling in an expansion stage. Expansion device. And then 4 to 1, basically right here we can see that its heat addition is happening, right? So in evaporator, so it's also constant pressure heat addition. Constant pressure heat addition, or heat absorption. Right? So those are basic four thermodynamic process is happening in between this refrigeration cycle. Let's take a look at the TS diagram, right? So this is the saturated dome, right? So basically we see that compressor inlet is the saturated vapor. So 1 to 2, it would be like this. So this is number 1, this is number 2. Okay, and then from 2 to basically here 2 to 3 is that heat rejection, right? So heat rejection will be something like this. 2 to 3 heat rejection. And then 3 to 4, it's the expansion through the throttling valve, right? So it will be like this. It is not that expansion is not isentropic expansion, so that's why this line is curved, right? So 3 to 4. Okay, so that's the actual ideal ideal TS diagram of vapor compression refrigeration cycle. Yes. Okay. So this is the, however, I mean, in in we should see something like this if we use the turbine, but we don't see this one, right? This one we are using, we are expanding through a expanding through a expansion valve, so that's why we don't see this. So it will not gonna be like that. Okay. So, and also, what about the pH diagram? So here, instead of using the PV diagram, we will use the pH diagram a lot, right? So the pH diagram, let me remove it. In the refrigeration cycle, the pressure versus enthalpy diagram will look like this. Okay. I exaggerated it a little bit. Okay, so it will be look like this. So basically 1 to 2 is here, pressure is increasing in the compressor, and 2 to 3 here, 1 2 3, and then 4 to 5 it's basically constant enthalpy. 3 to 4 constant enthalpy, right? And 4 to 1 it's basically here. So here it's that heat rejection, which is Q. Here is the heat rejection, which is QH, and then here is the heat addition, which is QL, right? Same goes to here, QH and QL. Okay. And also this is W compressor. Actually it will be inward. So this is W compressor, and yeah, that's the work input, and here as well W compressor. Okay, so that's the pH diagram. So now let's take a look at the energy balance equation. So basically the energy balance equation would be energy balance would be Q in minus Q out, right, plus W in minus W out equals to exit enthalpy minus inlet enthalpy or input enthalpy, right? So for this refrigeration cycle, so basically that's all about the the energy balance equation. However, if we want to see that what is the Q in or what is the QL, Q in or QL equals to nothing but H1 minus H4, right? And then Q out or QH, heat rejection, basically that one is H2 minus H3, and then W net work of this cycle is, I mean, basically the work is consumed by the pump, right? Sorry, the compressor, right, which is in, and that work input is equals to H2 minus H1. So we know pretty much all of the term. We can determine the coefficient of performance, right? So we saw in the last class definition of the coefficient of performance of the refrigerator equals to QL divided by W in. So QL we know here it's H1 minus H4 divided by W in, H2 minus H1. Similarly, if we have a heat pump, right, instead of a refrigerator, the cope of heat pump would be QH divided by W in, and then that would be H2 minus H3 divided by H2 minus H1. So we know that coefficient of performance, again guys, we are not gonna use the efficiency term anymore in this chapter, so we'll use this coefficient of performance. So now we know that ideal cycle, right, and we know the energy balance equation. Also we know that coefficient of performance, right? So let's take a look what is happening in the actual cycle, or what are the limitation in ideal cases. Okay, So in actual vapor compression refrigeration cycle, let me let me write it one more time about this one. Okay. Okay. So this is the ideal case, right? In ideal refrigeration cycle or the vapor compression refrigeration cycle. So let's take a look what are the difficulties it's happening here or in the TS diagram. So basically in refrigeration cycle, the refrigerant is the working fluid, and it has two phase, right? One is that liquid phase and another is the vapor phase. So when this liquid phase and vapor phase, it's alternatively changing within these devices, four key components of this VCR cycle. Then basically what is happening that when it's passing through these ducts or pipes, basically it's losing the pressure, or it's due to the friction, some sort of loss is happening in these pipes connection. So how we can consider or acknowledge those losses in the TS diagram? So that's what we are gonna take a look, right? So in the actual TS diagram, we will see that this is the DOM. Okay, in the actual TS diagram, basically the compressor inlet is not completely saturated vapor. It's mostly it's superheated, right? Somewhat superheated. So superheated means that it's outside of this saturated dome right here. Okay, and then the compressor is basically, if we think about this, compressor is basically increasing the pressure and, excuse me, 1 to 2, excuse me, increasing the pressure and slightly the temperature as well. And then we in the ideal case we saw that excuse me, in ideal case we saw that this line is something like this. Okay, right? In actual case we see that this 1 2, if we consider this one as a 2 prime actual case, the pressure is, or that line is something like this. Okay, this is 2 prime, 2 prime. And then from 2 to 3, if we consider this point as a 3, this pipe, right, 2 to 3, this pipe, basically we'll see that there will be some loss, right? So 2 to 3, so there will be some there will be some loss. I mean, temperature will slightly decrease, right? As well as pressure will remain constant, however temperature will slightly decrease. But in actual case, if we see that the pressure will not gonna be up to this point, ideal point, the pressure will be, or the temperature will also decrease, right? Due to this long duct, it has some, I mean, we have to somehow insulate this duct. Anyway, so and then from 2 to basically, if we consider this point as a 4, right, 2 to 4, we will see that this it will follow this constant pressure line, or the constant pressure heat rejection, 2 to 4, right here, right, or 3 to 4, whatever you say. And then 4 to, if you consider this one as a 5, just inlet of the expansion valve, it already loses some, or it already subcooled by some some couple of degrees of Celsius. So in that case it subcooled by like this, so it will be 0.5 within this pipe. So this is the this pipe section. Okay, and then from 5 to, if you consider this one as a 6, so the 5 to 6 is basically this expansion is happening. Okay, and then from 6 to 7, if you consider this pipeline, okay, 6 to 7, it will further lose the pressure or drop the pressure, right? So it would be 6, excuse me, so it would be 6, and then this point would be 7, and then 7 to 8, it will look like somewhat like this, and then 8 to 1, 8 means this point. Okay, and 8 to 1 is this pipe, and this is 8 and this is 7. Okay, so now we'll see that there is slightly difference between these two pressure lines. So the pressure drop is happening in 6 to 7, I mean this duct, and then pressure drop is happening in this line, right? So this is not a constant pressure. Some the heat rejection is somewhat uh, pressure is dropping as well in this condenser. So that's the actually the difference between the actual cycle and ideal cycle. We see that the compression is not perfectly or not completely the isentropic, as well as the heat rejection is not a constant pressure. So this is the heat rejection QH, and this is the heat addition, right, QL. And we also see that the heat addition is not not a constant pressure as well. So there is a slight pressure drop in the heat rejection and the heat addition or heat absorption process. So that's the difference between the actual cycle and ideal cycle. That's all about today's class, but I would like to mention that your homework would be that the read the topic 11.4 to better understand, or to go over the points of all of this we discussed, like how the pressure piping loss or the pressure loss in these ducts or pipe is happening, right? So just to better understanding or go over all of this individual pipes. So anyway, so that's all about today's topic. So we talked about the ideal vapor compression refrigeration cycle and also the actual vapor compression refrigeration cycle. So we'll go ahead and solve a math problem based on this. Thanks for watching this video. We'll come back with the math problem.